In this tutorial, you are going to prepare to learn how to calculate empirical and molecular formulas. Now, you don't really know what those are yet, but before we get to them, we have to review a few things. You need to understand the definition of molar mass. You need to be able to calculate molar mass. You need to learn to convert between moles and mass. We've done all of those things before, so we'll be reviewing those. You also learn to calculate the mass percent of an element in a compound. In the last chapter, you learned how atoms form bonds, ionic and covalent. You learned how to write formulas. You learned how to name compounds. And before this, you had learned how to count the atoms in compounds. But did you ever wonder how scientists came up with these formulas? How do we know that sugar is C6H12O6? Well, that's what we're going to learn. It all starts off by thinking about how we even figure out how many atoms there are. First off, we have to remember that atoms have very tiny masses, so scientists had to come up with a unit to avoid using very small numbers. If you remember, Lavoisier did a bunch of very careful experiments in which he weighed elements before and after reactions, and he could figure out, to some extent, what was in those elements. But he couldn't measure atoms because they're too tiny. So they came up with the concept of the mole. This brings the measurements of tiny atoms down to a scale that we can work with. 1 mole of any substance contains 6 times 10 to the 23rd units of that substance, and that number is called Avogadro's number. For instance, silver has an atomic mass of 107.9 atomic mass units. Well, if you have 6 times 10 to the 23rd atoms of that, you have 107.9 grams of silver. Likewise, lead has 207.2 atomic mass units, and if you have 6 times 10 to the 23rd atoms, you have 207.2 grams. Notice I'm shortening Avogadro's number. It really is 6.022 times 10 to the 23rd atoms. So, more examples of the mole. In all of these, you see that in every one of these examples, we have Avogadro's number of atoms present, 6.022 times 10 to the 23rd. But the mass of each sample is different. The mass is measurable in a laboratory, and it lets us relate measurable quantities, masses, to the number of atoms so that we can figure out chemical reactions and chemical formulas. The average atomic mass of an element is the weighted average of the masses of all the isotopes of the element. You find this on the periodic table. I would like you, in this class, to use digits to the hundredths place for all problems. For instance, oxygen would be 16.00 grams per mole. And yes, those zeros are significant. Remember significant digits? Hydrogen will be 1.01 grams per mole. Sometimes in the demo problems, I'll round the values so you can see the concept more easily and not get bogged down in numbers. But I want you to use values to the hundredths place. Here are some examples of how we got those numbers. If you look at your periodic table, you will see that oxygen is 15.9994 grams per mole, but I want you to use it to the hundredths place. So you need to round to the hundredths. That's the 9 with the line under it. You have to look to the digit to the right, which is also a 9, which is going to round things up until you get 16.00 grams per mole. Hydrogen is 1.0079 grams per mole, rounding to the hundredths place. You look at the 7 and round the hundredths place up to 1. If you have 2 oxygens, since it's diatomic, you simply multiply those masses and you get 32.00 grams per mole. Hydrogen 2.02 grams per mole. Now, in calculating molar mass, you have to remember that a compound is a collection of atoms bound together. Here's one that is 1 carbon and 4 atoms. This is methane. This is the stuff they're pulling out of the ground when they're fracking. You get the molar mass of it by summing the masses of all of the component atoms. 1 mole of carbon, 1 times 12.01 grams. 4 moles of hydrogen. Now look here at this example from your book, uses to the thousandths place. They always use 4 significant digits. So they come up with 16.04 grams. Now notice, if you follow the directions I gave you, you're going to have a slightly different value for the mass of hydrogen, 4.04 grams. You're going to have a slightly different answer. That's acceptable. And the reason I ask you to stick to the hundredths place is you won't be thrown off when our answers are a little bit apart just due to rounding. We'll come up with the same answer. Let's work on water. 2 hydrogens, 2 times 1.01 grams. We can measure this in atomic mass units or grams per mole. And oxygen, 16.00. Atomic mass units or grams per mole. Add them together, 18.02 atomic mass units or grams per mole. The molar mass of water is 18.02 grams per mole. Here's one that's a little harder, but it's the same idea no matter how many elements you have in it. 6 carbons, 12 hydrogens, 6 oxygens, add them together, 180.18 grams per mole. Again, if you look this up in a reference book, you might get a slightly different value because they use a slightly different value for hydrogen. Just be aware of that so you don't think you're wrong when it's just a rounding error. We can do molar mass for ionic compounds as well. Sodium chloride. Add the mass of 1 sodium atom to the mass of 1 chlorine atom, and you get the molar mass of sodium chloride. It's the same idea. Here's an example which will remind you how to count atoms when there are polyatomic ions involved. 1 magnesium, 24.31 grams per mole. 2 oxygens. Why are there 2 oxygens? Well, the subscript 2 relates to everything within the parentheses that are right in front of it. So you have 2 oxygen, 2 times 16. You also have 2 hydrogens. Why? Well, because that 2 relates to the hydrogens because they are also within that parentheses. Please notice that the 2 does not relate to the magnesium. It is not within the parentheses. Add all those up, you get 58.33 grams per mole. Here are some other examples. An atom of nitrogen, an element, is 14.01 grams per mole, straight from the periodic table. But nitrogen forms a diatomic molecule. So it's really N2 most of the time when it's not bonded to something else. So you multiply that value by 2, 28.02. Water is a molecule. We already calculated that. Barium nitrate is done much the same way as we did the magnesium hydroxide. 1 barium, 2 nitrogens, 6 oxygens. Add up to 1 formula unit of barium nitrate at 261.35 grams per mole. Now, here we're getting to what we wanted to learn in the first place, percent composition of compounds. The percent composition consists of the mass percent of each element in a compound. Well, what does that mean? Well, it's like any percentage. It's the part over the whole times 100%. If you score 48 out of 50 on a test, you have 96%. You get that. We're doing the same thing here, except we're talking about elements within a compound. It's the mass of a given element divided by the mass of the compound times 100%. Here's an example for iron 3 oxide, ferric oxide. This is rust, basically. Okay? We want to know the percent iron in rust. Why? Well, maybe somebody wants to come up with some recovery method so that from a big pile of rust you can get the iron out and reuse it. So they want to know how much iron can I expect to recover from this big pile of rust. So, what do? Well, we calculate the percent from the formula. We know the formula of rust, ferric oxide, iron 3 oxide, is Fe2O3. So we figure out the mass of the whole thing, 2 irons, 3 oxygens. And we figure out the mass of the iron in 1 mole of that, 2 irons. We divide the iron part by the iron 3 oxide total, multiply by 100%, and we get 69.64%. Now suppose we also wanted to know how much oxygen we had. Well, but there's two ways to do it. We can do it the way we just did it for iron, except put in the 3 oxygens and divide them by the total mass and get multiply by 100% and get 30.06%. Or, since there are only 2 elements in this compound, you can take 100% the whole, subtract the 69.94%, which is iron, and you come up with 30.06%. The percentages should add up to 100%, and this is a way to check your work. We can also calculate the percent composition from masses of each element. Scientists do the actual masses obtained in experiments. This is really a very important research tool. If a scientist discovers a new compound and they want to figure out what it is, they'll break it down, measure the mass of each element that they identify in it. Here's an example. A new compound is extracted from a plant root. It breaks down as shown below. What is its percent composition? Well, figuring this out will help us figure out the formulas of the new compound. We're going to remember the part divided by the whole times 100% for each component. So if we have 0.9480 grams of carbon and our whole sample was 0.2370 grams, part divided by whole times 100%, 40%. Do the same thing for the oxygen, the same thing for the hydrogen, and it should add up to 100%. Here's the breakdown of water. We're going to do this from the formula. 2 hydrogens, the mass of 2 hydrogens divided by the total mass times 100% gives you 11.21% hydrogen. 16 grams of oxygen divided by the total mass times 100%, 88.79% oxygen. Check. It should add up to 100%. Let's do this exercise just to kind of give you a little practice before you come to class tomorrow ready to do these problems. We have 4 compounds: water, laughing gas, we have 4 compounds here: water, N2O, C3H6O2, and carbon dioxide. And we want to figure out which one of these has the most oxygen by mass and which one has the least. So we have to do separate calculations. Let's do the math. I'm going to round these to whole numbers to make it go faster since we're at the end of this tutorial and you just need to see the idea. N2O, 2 nitrogens, 1 oxygen, 44 grams per mole. The oxygen is 36%. Water we just did, 89%. C3H6O2. The percent to this works out to be 43%. And the carbon dioxide, the percentage works out to be 73%. You can take a minute, pause it, look at those calculations to make sure you understand them. And now we're simply going to rank these to answer the question. Water, highest at 89%. Carbon dioxide, next at 73%. C3H6O2, third. And N2O, fourth. And that's the end of this tutorial. Come to class tomorrow ready to do problems like this. And thank you for listening.